In today's lesson, we're going to study section 3.9, which is the derivatives of exponential and logarithmic functions. I've decided to break this section into two parts, so today we'll just study the first part, derivatives of exponential functions. If you recall from pre-calculus 30, exponential functions are functions of the form y equals b to the x, where b can be the base of any positive number except 1. We have two different types of exponential functions listed here. The first one, you notice the base is greater than 1. And when the base is greater than 1, we get a function that is increasing. So the graph of our exponential function will be going uphill. When we get an equation where the base is between 0 and 1, we'll get a graph that is decreasing. And if you recall from pre-calc 30, that graph will be going downhill. In calculus, we also deal with a special number called e. It's a constant, and e is defined as 2.71828, etc., etc. And the graph of e is shown for you. This graph also represents the graph of any increasing exponential function. So whether the base is 2, 3, the graph will be very similar. Just the steepness of how much it increases will change with the difference in the base. Today we're going to learn how to take the derivatives of exponential functions that have a base e, which is our special constant, and ones we'll call base a, which is any number other than e. So let's go through a specific example, and then we'll look at the actual rule for taking the derivative, or the general rule for taking the derivative of an exponential function. So we have the example y equals 5 raised to the 3x. When we take the derivative of this, there's actually three parts to it. The first part is to take the derivative of any exponential is going to be itself, so it's going to be 5 to the 3x. Then we will multiply it by the derivative of the exponent, which in this case is 3, and then we will multiply it by the natural logarithm, which is denoted by ln of the base, which is 5. Now ln 5 is just a decimal number you get on your calculator, but in calculus we like to leave it as an exact form. So if we write our final answer, lots of times what happens is we will write it as 3 ln 5 and the function 5 to the 3x. And that would be your final answer. Okay? So again, when we take the derivative of an exponential function, it's itself times the derivative of the exponent times the natural logarithm of the base. So those are the three parts to taking the derivative of an exponential function. So in general, let's just maybe write ourselves the general definition before we get to our next example. If we have the following, y equals a raised to the u, and we want to find dy dx, which is the derivative of u, or y with respect to x. The three-step process would be it's itself, which is a to the u, times the derivative of u with respect to x, times the natural log of the base, which in this case would be a. Now, for our next example, we have 17 raised to the 4x squared. Clearly, it's an exponential function with base 17. So to find the derivative, f prime, it's going to be itself, so 17 raised to the 4x squared, times the derivative of the exponent, which is 8x, times the natural log of the base, which is 17. Now, looking at exponential functions with base e, no pun intended, but these are even easier, okay? You take the derivative, we'll go through a specific example, and then we'll look at the general definition. So for the specific example, it's again y prime is equal to itself times the derivative of the exponent, which is 3, times the natural log of the base. Now, when our base is e, we are not required to show this last step, ln e, the natural log of the base, because ln e has a value equal to 1. And the reason that is the natural logarithm ln is really log base e, and then when I have the number e inside that logarithm, if you recall from pre-calc 30, e, a base of e of a number e raised to the 1, the answer is just that exponent, but all you really need to know is ln e is equal to 1, so you don't have to write the ln e part. So therefore, in general, if we wanted to make a general equation again for taking the derivative of base e, if we have e raised to the u, y prime is going to be equal to itself, e to the u, times du with respect to x. All right, let's take a look at one more example. And we have, in this case, f of x is equal to e raised to the 4x squared plus 3x. So when I take the derivative, f prime, it's going to be itself, so e raised to the 4x squared plus 3x, times the derivative of the exponent. And the derivative of the exponent is I'll erase that. The derivative of the exponent is 8x plus 3. Now, some of you may be wondering, why am I using brackets? And I'll just highlight the brackets in red here. The reason I put brackets around 8x plus 3 is I want to make sure that this whole base, or the whole function itself, is multiplied by 8x plus 3. If we read it like this, without the brackets, then mathematically we're saying that 8x is just being multiplied by our exponential function and we're adding 3 at the end. So this is incorrect. So our final answer for this particular question is going to be this guy right up here. All right, we'll continue with some of the more complicated exponential functions and their derivatives in class, but I hope this lesson made sense, and we'll see you in class tomorrow.